So our first optimization problems deal with what I'm terming distance optimization problems. I don't think I spelled optimization right there, but all right, so we're going to be doing that. And so let me go ahead and draw a picture of the situation and explain what's going on. And I think once you see what's going on, you'll kind of see that there's a pattern. So what we're going to do is first let P be a point on the graph of y equals 2x plus 5. So let's draw a picture of that. So I'm going to go, let's make a grid, and we're passing through 0, 5, and we have a slope of 2. So we're going to go 2 up and 1 over, 2 up and 1 over, right? 2 down and 1 over, 2 down and 1 over. So we basically have that line, all right? There's the line y equals 2x plus 5. So P is a point on that line. So maybe P is here, maybe P is here, maybe P is there, but it's just some ordered pair that lies on the line y equals 2x plus 5. So in terms of our language, this is essentially our constraint. Okay, we are only, there's a bunch of other points in the xy plane, but we're only considering the ones that are on this line. So there's that picture. All right, and what they want us to do is to find an expression for the distance from any point, so any point on this line, to the origin 0, 0. So let me change colors here. All right, so let me go to black. Hopefully that'll show up fine. So there's 0, 0. So what I'm basically trying to do, let me put this in red, is at any point, I am basically trying to find that distance from that point or that point or that point. Notice the distance is constantly changing. It gets really long at some cases, gets pretty short in some other cases, and gets long in some other cases. But as we move along this line, y equals 2x plus 5, the distance keeps changing. And it's basically a function, right? Because 1 point gives us one distance, right? So 1 point gives us some distance. 1 point gives us some distance. So it behaves functionally. And so our charge is to basically find an expression for that distance. I give you the point, then you can basically find the distance by plugging the point in there. And then the challenge, though, is I want that function to be a function of x only, not of x and y. All right, so there's what's happening. And what we're going to do is, since we're basically, no matter what the point is, let's remember what our distance formula is if we're going from x1 to y1 to x2 to y2. All right, a couple sections ago, we found that the distance is equal to x2 minus x1 squared plus y2 minus y1 squared. Oops, that parenthesis shouldn't be there. That was our distance formula. And so what we have, our x1, y1 is actually the origin, right? So that's one of our data points that's given, 0, 0. And then x2, y2, I'm just going to call them x and y, because x and y is basically some data point that's on that graph. And so putting that information in here, we get that d is x minus 0 squared and y minus 0 squared. And so at this juncture, we have d is equal to the square root of x squared plus y squared. So there is basically the function that we're going to eventually try to minimize and optimize, but we're based off of this constraint. So at this stage, you'll notice that the distance depends on both x and y, the ordered pair. I just want it to be a function of x. And so we'll basically come over here and say, well, we know that y is 2x plus 5. So replacing this y with that, we end up with the square root of x squared plus 2x plus 5 squared. And now we've got it. So there is our d of x. So at any point along the p value, or at any point p along the line, all I need to give you is the x coordinate. X is 1, x is 2, x is 3, x is 4. And I'll plug it into this formula, and I basically have the distance. So there is our function that we basically can use to find the distance. And that's what I'm asking us to do in the next step, right? What is the distance when x is equal to 1? So all I got to do is find d of 1. So plugging that in, we get 1 squared. We get 2 times 1 plus 5 squared. And I think that's 1 2 plus 5 is 7 squared, so we get 1 plus 49, and we basically get the square root of 50. And using some previous knowledge, I think that reduces to 5 square roots of 2. So when x is equal to 1, and I've got a lot of drawings on this, but when x is equal to 1, so let's say that's 1 right there, right? My value is equal to 7. So the distance, that distance right there that I'm putting heavily in blue, that distance is 5 square roots of 2. And so if I give you another x value, like if I said x was equal to -3, I'd be coming back this way, right? And then finding the distance from the origin to that point on the graph where x is equal to 3. So that's essentially what's happening in all these distance problems. We've got a point that's fixed. In this case, it's the origin. And we have another point that's following some curve, and we're trying to find the distance between those two guys. All right? And so our next question now is there values of x that makes this the smallest? And I think visually we can see that does in fact happen. All right, somewhere probably around -1, all right, there is a distance where the distance between the origin and a point on the line is at its very smallest. So we can physically just see that from the graph. Now, is it exactly -1? We don't know. We've got to analyze the graph. And this is where our graphing calculator is going to kick in. So we're basically going to pull the graphing calculator out. All right. And let me get to y equals, clear some stuff out that I had previously. And what we're going to basically do is plug in our formula that we have. Let me try to get that in there really nice. All right, so trying to get everything all in this thing without all these glares has always been a challenge. All right, so we're going to plug in our distance formula. So we've got a square root, and underneath that square root we have x squared. And then we have plus parentheses 2x plus 5. We're going to square that, and I think that's everything underneath that radical. And why don't we go ahead and we'll graph this. So I think my standard viewing rectangle, oops, you know what? I've got a whole bunch of stuff there. Let's go to zoom and standard. So there's our graph. And what we're looking at is, again, this is the distance a point is from 0, 0. And you do see that there, in fact, is a minimum. And I was a little bit off because it looks like that minimum is occurring right around -2. So graphically speaking, you know, if this was a homework problem, you'd basically tell me, you know, what you inputted. And then you'd show me on your graph that this is what you're looking at. And we're looking at that point right there. And, of course, the calculator will find that point for us. So all I've got to do is go to second calc. We're going to actually find a minimum, so I'll highlight minimum. And I got to go to the left of that minimum, so I'm going to press the left arrow. Notice my little cursor moving. I'm definitely to the left of that low point. And that's going to ask me to go to the right. So I'm now definitely to the right. And then it's going to ask for a guess. So that looks about good. Oops. Maybe right there. Press enter, and what it returns for me is that x is about -1.99999, which we know to be -2. All right, so we're getting -1.99999, but I'm really kind of guesstimating that that's -2. Okay, so at -2 is where we're at our lowest. So again, looking at our graph, I think my grid was just off a little bit, right? At x equals to -2, that's where the minimum distance is going to be. Of course, what's also nice is because the y value is giving, it's actually telling me what that distance is. That distance in this case, at x equals to 2, the distance is roughly, what did it say? Let's just say 236. So 2.236. So not only do I know the location on the graph, x equals 2, I can even find my y value, right? I think y is equal to 1. We're there. So at the point -2, 1, right, my graph is at its minimum distance. And it'll be basically 2.236 away. And so that is how you do those distance problems. They're always going to have our distance formula. You plug in the data points that are given for the problem. That's going to give us the function to minimize. You're going to be given some sort of a constraint equation. You use that to replace y, and that basically gives you your function. And you can answer any questions. You can find specific values. You can find high points or low points. And again, because we're not, I know that looks quadratic, but we know it's not, right? Because of just looking at the function. That's a pretty unquadratic function. It just happens to look somewhat parabolic. Alrighty, so there you have it. Let's do some more problems where we practice this skill and get you guys ready for your homework.